Okay, welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to have Lance Dixon come and join us from Stanford. Lance did a BS in Physics and Applied Mathematics at Caltech, and then did a Master's and PhD at Princeton before he came across to SLAC to do his postdoc. He stayed at SLAC after his postdoc and is now a professor there, has been since 1998. Lance is a theoretical elementary particle physics professor. He is very interested in Higgs boson physics and also has been recently working on standard model backgrounds for particle physics at the LHC. He is also interested in perturbative relations between gauge theory and gravity. And today he's going to talk to us about alternatives to string theory to talk about quantum gravity. So if you'll join me in welcoming Lance.
All right, thanks a lot, Adrian. Thanks for the invitation to visit. Found this to be a pretty fascinating place on my short whirlwind tour earlier. I have to say my background isn't too close to, say, SETI or planetary science, but my father was an engineer who used to come up to NASA Ames all the time because in the late 60s he worked on the Pioneer projects that went to Jupiter. And so it's possible that there is a little bit of a SETI connection there because he might have told Carl Sagan where he could bolt his plaque on to the Pioneer spacecraft. So anyway, what I'd like to do today is to tell you a little bit about some work that I've been doing with my collaborators on the idea that maybe there are some theories out there that can help make gravity consistent with quantum mechanics. And string theory is a theory of everything, which actually does a very good job of making gravity consistent with quantum mechanics. But as we'll see, it also has other sort of baggage it comes along with. And the question is, are there some maybe simpler theories that could also do the job? And we don't know that there's any way in which they can replace string theory, but we're just interested in knowing what all the possibilities are. So that's what I want to tell you about today. But to step back a bit, of course, gravity is the force which is the most obvious in the macroscopic universe, in the cosmos. It governs all the orbits of all the luminous and dark matter that you don't see there. And it really controls everything on the largest length scales. But it's actually a very weak force if you measure it on a per particle basis. What you see here is a tug of war between electromagnetism and gravity. Gravity is trying with the might of all the Earth to pull these paper clips down. And this little tiny magnet here is able to resist it. So obviously electromagnetism is a lot stronger than gravity on a per particle basis. And indeed, gravity is really the weakest of the forces at macroscopic distances. Now, another big principle that we have in physics is quantum mechanics. And quantum mechanics rules not the cosmos so much, but the very small. It's really only very evident when you go to short distances, say atoms here, where you have these little corrals in which you can trap electrons and get nice wave functions here. And you can also, of course, see that light behaves as a wave when you diffract it through these two slits. But we also know that the duality of quantum mechanics is that light is a wave, but if you read correctly, you can see that light is also a particle. So we have this kind of duality between particles and waves in quantum mechanics that governs everything we think about there. So the question we want to ask today is, how can gravity and quantum mechanics coexist? And since Einstein, physicists have sought to unify all the fundamental forces in particles in the universe, and they've been quite successful in many respects. Three of the forces that we know about, the strong and weak forces, which are most evident inside the atomic nucleus, and electromagnetism, which is another long-range force like gravity, they've been put on a common footing, which is fully consistent with quantum mechanics, also completely consistent with special relativity. And this framework is not only very theoretically appealing, but what makes it most appealing is that it passes a tremendous number of experimental tests every day. Gravity, the fourth known force, is very different, though. It's different in a couple of different ways. In some sense, it's the most universal force of all. It couples in exactly the same way to every particle or collection of particles. It really only cares about the energy and the momentum of the particles, basically. Whereas the other forces act very differently on different kinds of particles. For example, the strong force, electrons don't feel it at all, while they feel the electromagnetic force. Neutrinos don't feel the strong force or the electromagnetic force. They only feel the weak force. But every particle, we believe, feels gravity. Another difference has to do with when we consider these forces to be carried by particles. We can ask, how much are these particles spinning? And for the strong, weak, and electromagnetic forces, the answer is that they spin with 1 unit in some basic unit, which is called Planck's constant. Whereas the graviton, which carries the force of gravity, has twice that spin. So it's quite unusual in that respect. It's actually connected in some way to the first property. And while gravity is extremely weak at very large distances where we can see its effects, when we try to build a theory of it based on Einstein's theory of relativity and to promote it into a quantum theory, we find that although it's very weak at very long distances and low energies, when we go to very high energy collisions, it should become very strong. And part of the problem of the coexistence between gravity and quantum mechanics is that it seems so strong that it leads to inconsistencies or infinities that we can't get rid of. So that's going to be some more of the theme of this talk. Now, the other theory mentioned in the title is superstring theory. And superstring theory posits that all of the particles that we see around us, or see through collisions in laboratories, if we don't see them directly, since they're all pretty small to see directly, but all of them are made out of strings. So this is a microscopic view of the proton, and the structure of the proton was unveiled up at SLAC in the late 60s directly by bouncing electrons off the proton. It was deduced that the proton was made out of quarks. In some sense, it's made out of 2 up quarks and a down quark. And that's if you go to very short distances, like 10 to the minus 15 of a meter. But string theory says that if you go several another 10 to the 18 orders of magnitude, 19 orders of magnitude below the size of the proton, then these quarks themselves are no longer point particles. Instead, they are just strings vibrating in a particular way. And these strings could be vibrating in free space. They might be attached to some other kind of surface in space-time, and so on. And so string theory is a sort of radical change in how we view particles, maybe even more radical than the notion 40 years ago that the proton was not an elementary particle, but was made of smaller elementary particles. And in string theory, the way particles interact is actually somewhat different than how we think of particles interacting when we think of them as point-like particles. Point-like particles tend to interact, well, classically you think of them as bouncing off each other, but when we think of forces, we often think of them as exchanging other particles too. But those particles tend to touch each other. And in the case of strings, the strings are spread out, so they also interact by things touching and joining and then breaking up. But the interaction is sort of smeared out a bit more. If you see a couple strings here, they can interact by joining if they're open strings, or an open string can form a closed string, or two closed strings can merge into one, or break up again. And this picture over here shows a closed string splitting into two closed strings as you move in time from left to right. But when you sweep out what the bits of string are doing, there's a one-dimensional string, but as it moves in time, it sweeps out a two-dimensional surface. And this surface is a smooth surface, so there is no real one point there that you can say where some interaction happens. So things get smeared out in space-time. And that's more or less the way that gravity helps to be consistent with quantum mechanics within the framework of string theory. But we'll come back and look at that again from a little bit different perspective in a moment. So, but the point is that this sort of changes the high energy behavior of particle interactions a lot. What I want to do in this talk is to describe another possible way that quantum gravity might work without using strings and using only point-like particles, like the theories that have so successfully worked for the strong, weak, and electromagnetic interactions. And we've been studying a particular theory because among point-particle theories, it's the most obviously well-behaved. It was invented a long time ago in 1979. We don't think it's by itself a theory of the whole universe. We think of it as a toy model to see whether we can make point particles consistent with gravity and quantum mechanics. And what we found over the past decade or more is that it is a much better behaved than was previously thought. And it still might well turn out to be inconsistent or impossible to make realistic. So we don't know the final answer to the question in the title. But along the way, we've learned some interesting things about point-like theories of gravity and how they're related to these other theories of the strong, weak, and electromagnetic interactions. Now, I should say that there's been lots and lots of studies of gravity and quantum mechanics together. For example, the radiation that was discovered by Stephen Hawking in the vicinity of a black hole is an example of an effect that involves both quantum mechanics and gravity. And in that particles are produced by quantum fluctuations in other fields, not the gravitational field, but in a sort of static, curved gravitational background. So there's a sense in which this could be called quantum gravity, but it's not quite the same in that the gravitational field is treated classically and doesn't tend to fluctuate very much. Instead, there's sort of ordinary particles that are being produced because of the very large curvature and strong gravitational fields. Another notion, which is closer to what I think of when you say quantum gravity, is space-time foam. So the idea is that in quantum mechanics, nothing is certain. Things can fluctuate in different ways. And gravity, Einstein told us that gravity is not just a force, it's also a notion of how space-time curves in response to matter and how things bend and move along various trajectories. So when you make gravity quantum mechanical, the space-time should be allowed to fluctuate somehow. And so if you look on very large scales, you don't see this at all. But when you get to these same sort of microscopic scales at which we were talking about before, tens of orders of magnitude below the size of the proton, then you might see this fluctuation in the background geometry. Now, some of this is very hard to get under control. We're going to sort of move a little bit in this direction, and we're going to take the quantized plane wave ripples of space-time that correspond to gravitational waves that are called gravitons, and we're going to imagine that they are just baby versions of these fluctuations, and we're going to scatter them off each other, and we're going to investigate this scattering theoretically and see what we can learn about the consistency of quantum mechanical theories of gravity. Before we get to that, let me just remind you a little more about electromagnetism. I'm sure most of you know it's the force that holds atoms together, and in radiation it manifests itself, as electricity and magnetism, and also in radiation as light, and of course the radio waves that are the key to SETI. And it's carried by the photon. The photon is the particle that is a packet of light. And it's the embodiment of the statement that light is not only a wave, but also a particle. So it's a plane wave ripple of an electromagnetic field, a quantum unit of it. And we can study the dynamics of electromagnetism at the quantum level. As I was mentioning before, there's a very precise theory of how particles behave under the electrodynamic force. And it's called quantum electrodynamics, or QED. And it's consistent with quantum mechanics, special relativity, and of course all the tenets of electromagnetism. So this theory describes the interaction of its key participants, photons and electrons, as well as other particles, to incredible accuracy. And a lot of the framework for analyzing it was developed in the 1940s by Richard Feynman, as well as Tominaga and Schwinger, who got the Nobel Prize for their early predictions in quantum electrodynamics. But Feynman also developed a diagrammatic language for describing particle interactions in general, which is so powerful that it earned him a place on a postage stamp. So I'll show you a few of these diagrams. But what they do is they tell you how to compute processes to as high a precision as you want, or at least as high a precision as your computer is capable of, one of the two. And the rules that Feynman gave was that you draw a set of diagrams with certain rules which we'll just sort of exhibit by example. And they have a certain number of closed loops in them. And the loops indicate how important the diagram is, or how big the number is that's associated with it. And that's a good thing, because if you had to draw every possible diagram, that's uncountably many. Well, countably, but infinite. So the fact that the ones with more closed loops are suppressed by a small number makes it possible to get to high accuracy very quickly. In the case of QED, the small number is called, well, it's the electric charge squared divided by 4 pi, but we usually call it alpha. And it's this fundamental constant, 1 over 137. So at the simplest level, an electron will interact with a photon by scattering, emitting or absorbing it through this vertex here with this charge E. But if we want to describe it more accurately, we have to include more graphs where we also have what are called virtual photons that interact with the electron at the same time. So it's the same process because it has an electron, and a photon on the outside. But now we have one more of these closed loops. So this one is smaller. It has actually 3 powers of E, or E times alpha. So it's smaller by roughly a factor of 137. And that's called the one-loop approximation. And if you want even more accuracy, well, you just start drawing all the diagrams that have 2 loops in them. And I've shown a few of them here. But those are down by 2 powers of 137, or they're about 10 to the 4 times smaller than the leading term. So it doesn't take very long in this series to get incredible accuracy. In fact, there's a prediction that's been made for something called the anomalous magnetic moment of the electron, which has been computed theoretically by going to 1 loop, 2 loop, 3 loop, 4 loop. By the time you get to 4 loops, the kind of accuracy you get is about 10 digits of accuracy, about 1 part in 10 billion or something. And remarkably, experimentalists can also measure the same quantity to the same accuracy, and they get impeccable agreement. So QED is probably the most precise theory we have as a fundamental theory of the way particles interact. And it's basically understood at the 4-loop level. Now, QED is embedded into a bigger theory that we have of particle interactions called the Standard Model. And the Standard Model has in it all of the forces except conspicuously absent is gravity. It has electromagnetism and the strong and weak nuclear forces. And there's a sense in which these forces are just some kind of generalization of this force. You can see I drew some Feynman diagrams for these forces that look very similar to the Feynman diagrams for quantum electrodynamics. So when quarks scatter off each other through the strong force, they exchange a particle called the gluon, the carrier of the strong force. which is the analog of the photon over here. And when a neutron decays into a proton, maybe it's inside a nucleus, that's what we call beta decay. It emits a virtual particle called a W, the charged weak boson, which gives off an electron or a positron. So, and these interactions, there's a sense in which they can all be described in the same mathematical framework. In fact, we call this theory gauge theory because there's a certain notion of an invariance under changing the dials on a gauge. But anyway, it's just a name. Gauge theory is the theory that underlies the entire Standard Model and the interactions of what we call spin-1 vector bosons. All these particles have the same spin. And just like in QED, you can get finite testable predictions for pretty much any quantity you want to compute after a certain procedure called renormalization. And it was Gerard de Tooft and Martinez Veltman showed how you could renormalize the electroweak theory, and that led to the Nobel Prize for the successful testing of that theory at high-energy colliders. But gravity is quite different. As we were saying, electromagnetism and the strong and weak interactions are vector forces. They are carried by spin-1 particles, and you're very familiar with polarized sunglasses. That kind of tells you there must be two different kinds of photons, because you can block half of them when you hold your polarizer this way and half when you hold them the other way. So there are two polarization states of photons. The radio astronomers know pretty well that you can use other bases too. If you have linearly polarized light, it can turn into circularly polarized light when it goes through some plasma or something. And so you can also talk about polarization that has kind of a screw sense to it. And the two states there are left and right-handed circular polarization. And those are the two states where the spin of the photon is one unit in the same direction or one unit in the opposite direction from the way it's going. So we have these two helicity or spin states. So gravity is different, though. The way that gravity propagates, it's not sort of plane polarization. It's what we call a tensor. It's a little more complicated. When gravity propagates, gravitons propagate, there are plane wave ripples in space-time, but they stretch the space in a particular way. And one polarization, it would do this very imperceptibly, but it would make a person a little bit thinner and a little bit taller, that polarization. And the opposite polarization makes the person a little bit fatter and a little bit shorter. And if you do the same transformation to think instead of in these kinds of XY polarizations, more like circular polarization, that turns out to correspond to a different spin. In this case, it corresponds to 2 units of spin. So gravity behaves differently from all the other forces. Now, one thing we can say is that in some sense, gravitons are real. Nobody's directly detected a graviton in the laboratory. In fact, nobody's even directly detected the classical analog of a graviton, gravitational waves. They've been looking in Hanford, Washington, and other locations. LIGO is a gravitational wave observatory. But what we do know is that gravitational waves have been emitted. They've been emitted from a particular binary pulsar system, which has spun down as the power from these gravitational waves was sucked out of it. And that's been tracked very well. Over here it shows the first 10 years or so of the tracking of that. And what it's compared to is the prediction from general relativity, which predicts very precisely how the orbits change as these gravitons are radiated outward in a classical radiation. So we know that the classical waves of gravitational emission must be there, or this prediction wouldn't have worked. Now those were classical waves, but now I'm going to use the license of quantum mechanics to say that the gravity is not only a wave, it's also a particle. And the reason I need to do that is that I want to tell you about what we're doing as theorists, even though they haven't really been observed in the laboratory, and that is to scatter these particles of gravity, these gravitons, off each other in order to see how different theories of quantum gravity behave. Before I do that, there's one other way in which gravity is very different that I need to tell you about. When we have a force of electromagnetism, the simplest configuration is just two charges sitting near each other, and they feel an attraction or repulsion depending on the sign of the charge. But that's proportional just to the charge of the objects. And it doesn't really depend on what frame you work in. That charge is a single number, no matter what angle or what speed you look at this from. And so it's very different from the case of Newton's law. In Newton's law, the thing that enters looks like the mass of the particles. Gravity produces a force proportional to the mass. But in reality, as Einstein realized when he built his theory of general relativity, what really goes into this force is not really the mass of the particles, but the rest energy. Through E equals mc squared, it kind of looks like the mass. But when these particles move, the thing that's really governing the force is not the rest mass, but the energy and momentum vector, which we often abbreviate by a little p that keeps track of 4 different pieces of it. Now we can come back again to this statement I made earlier about how weak gravity is. This is a kind of compressed graph. There are 44 orders of magnitude between here and here. So that's supposed to show you how weak gravity is if the paperclip didn't convince you of that. But that's just at very long distances or energies. What we know is that the real strength of gravity, because it couples to energy, it has an extra factor of E squared in it when we have very high energy particles coming at each other. And given enough energy, eventually that can become comparable to the other forces. The other forces are somewhat similar in nature. They're not all exactly the same magnitude. So the weak force is, well, the weakest. The strong force is the strongest. Electromagnetism is in between when you're in the subnuclear range. And we think they should all become about the same strength at some point. But this change is not very big compared to this incredible change here as you come and increase the energy by orders and orders of magnitude. And the special region for quantum gravity, if we live in a 4-dimensional world, is an energy which is 10 to the 19th times the mass of the proton, something we call the Planck mass. And that's also sort of not by accident the energy at which you might see these strings, these particles in string theory really being, you could really visualize the strings if you could go to those very high energies or those incredibly short distances. So now we're going to do a Gedanken experiment. So that's a thought experiment, which is really nothing more than mathematics. And as you recall, mathematics is the part of physics where the experiments are cheap. So it doesn't take too much to do this compared to building an LHC, for example. The way we're going to do it is we're going to just scatter these particles off each other. And these particles are moving at the speed of light, but we can imagine changing their energy. And the only real thing that happens in this thought experiment is you have 2 particles in and 2 particles out. And the scattering strength should depend on the energy. And we can also ask, how big are these corrections when we start to include these loops like we talked about in quantum electrodynamics? In this case, the loops are not suppressed by a fixed number like 1 over 137, but they're fixed by the gravitational coupling G times the energy. So this is a very small number if we were at small energies, but it could become very big at high energies. To do this, we follow Feynman's instructions and start to add up all of the Feynman diagrams. And this is what we call the scattering amplitude. It's the thing that you compute in quantum mechanics to work out the probability later. But it's built by adding up different terms, and these are supposed to indicate the different terms in the loop expansion. So at tree level, there are maybe 4 or 5 diagrams. And at the next loop order, well, we'll see some in a second, a lot more. And then at 2 loops, there are even more, and so on. So if we look inside the tree-level blobs, well, we see 4 diagrams. If we look inside the loop-level blob, we actually see 27 different diagrams. And then we start getting up into the thousands and millions as we go further. But in principle, we have a fixed set of rules, and we just have to work out all these diagrams. But when we do this, we find that there's quite a difference between how QED works when you scatter photons with electrons going around the loop, and how gravity works. Gravity couples to everything, but we could just imagine coupling it just to itself and just having gravitons in there. And what we find is that in quantum mechanics, we have to consider virtual particles, or states that aren't really allowed by energy and momentum but can exist for a short time. And in order to consider all the possibilities, we actually have to do a mathematical integral over the momentum being carried around by these virtual particles going around the loop. And this momentum integral is kind of dangerous. It might be infinite if this scattering is too big when this momentum gets very high. And you remember that graviton interactions get much bigger at higher energy. And that's exactly what happens. The Newton's law, when we take into account general relativity, or Einstein's theory of relativity, tells us we get powers of p squared up here, where over here we just got constants. And so we typically get worse behavior for this integral in the gravity case compared to the photon case. And so it's very dangerous, and this is one of the big reasons why gravity is very hard to make consistent with quantum mechanics. These extra powers of this virtual momentum. So the truth is that in quantum electrodynamics, these integrals just barely converge. And there are some other cases where they actually diverge, but there's a systematic procedure for getting rid of them by redefining some of the parameters of the theory. And this is the procedure called renormalization, which was applied to QED by Feynman, Tominaga, and Schwinger in the late 40s, and by 't Hooft and Veltman to sort of the rest of the standard model in the early 70s. But in the case of gravity, 't Hooft and Veltman also looked at this problem, and well, they realized that it was actually finite at 1 loop, but they kind of knew it was due to it was an accident. And then it took a little while longer before 2 groups, Goroff and Sagnotti and Van de Ven, looked at the same theory at the next loop order, and they found that there was a divergence which could not be fixed by this procedure of renormalization. And so the conclusion was that this pure gravity theory doesn't have any predictive power because it has these divergences which you cannot absorb into the theory and then get a certain number of infinitely many predictions after that. Or what we say more technically is that pure gravity is non-renormalizable, and that's the sense in which we really mean that it's inconsistent with quantum mechanics. In the meantime, string theory came along and became a candidate theory for everything. And it's sort of a kind of revolution in thought that goes from Newton and non-relativistic force of gravity to Einstein and space-time curving as a more accurate description of relativistic gravity, to quantum gravity, which was proposed back in the 70s. And then in superstring theory, we see that these sort of point-like diagrams get smeared out into strings. And this smearing out of the interactions makes these, what it does when you look at these momentum integrals is it damps them out, and it makes them finite. So string theory definitely works for removing these divergences. The question is that the only way to do it? And one of the string theory actually has many virtues, too many to list here, but it also has some issues. And one issue is something called the string landscape. There are a lot of different ways to go from a sort of ethereal string theory to something that looks something like the real world. In fact, the last estimate I heard about was that there were 10 to the 500 such ways to do this. 10 to the 500 different possible vacuum states or ground states or different kinds of universes that you can imagine. So the question is, do you think you can predict new phenomena if there are 10 to the 500 possibilities to choose from? So it's very challenging to do this unambiguously. Now, it could be that we get lucky and we see directly the evidence for strings. There are certain excitations of string theory, that certain massive particles that potentially could show up at the LHC. It's a little bit of a long shot, but it might happen. But if that doesn't happen, then we're sort of in the picture of trying to deduce the existence of string theory experimentally from very indirect information. So again, as I was saying before, we want to know whether string theory is really necessary for curing the divergences of quantum gravity. And the way it does it is it has this length scale at which you see the strings in the scattering process that smears things out. But it's a very different kind of notion. What we want to know is whether we can have just point particles that have their interaction so controlled by a certain kind of symmetry that while gravity naively looks poorly behaved, it's actually well behaved and consistent. So we've been using a symmetry that's called supersymmetry in order to do this. And we've been working in a toy model, but we think that if the results hold up, it will have a big impact on how we think about quantum gravity more generally. So what is supersymmetry? Well, I'm not going to be able to explain all the aspects to you, but it's basically a symmetry that relates different types of particles. In fact, it relates particles that have different types of spin. We were talking a lot about the force carriers, and I think I might have called them spin 1 bosons. So supersymmetry relates those kinds of particles to particles that have half-integer spin, or fermions. Those are actually the particles that make up matter, like electrons and quarks and stuff like that. So there's a version of supersymmetry, a phenomenological version that has exactly one of these supersymmetries in it. We call it n equals 1. And it predicts a host of new particles that may show up at the LHC, but time is running out. We'll see. Anyway, in this version, every particle we know is connected by one supersymmetry to another particle which is not yet observed. So there's a whole set of particles that are predicted by this theory, but in this particular version, they're supposed to show up soon, and they haven't. What we've actually been doing to get the most mileage on the theoretical side out of supersymmetry is we've been using the most possible supersymmetries you can really imagine, which is 8 of them. And this theory was built in the late 70s, and it has a very complicated a large number of different types of particles, but they're all related by this supersymmetry to each other. Every single particle is related to another one. These little arrows show you how you can go from a particle of gravity with +2 spin to 8 different particles, because there are 8 supersymmetries, with spin 3/2. And then you can use the 7 symmetries you didn't use the first time to go to the next stage and get 28 particles with spin 1, and so on. And the mathematicians among you will recognize this as some row in Pascal's triangle, but it adds up to 256 states, and they're all related by this symmetry. So they're all basically cousins of the graviton. And each symmetry changes you by 1/2 unit of helicity, and it has to take you all the way from a +2 helicity graviton to -2. So if you have 8 symmetries and a 1/2 unit at a time, that can take you all the way from 2 to -2. So in fact, that's why this is the most supersymmetry that's allowed if we don't have any particles with spin bigger than 2. And because of all this symmetry, the theory is extremely unique, but it's also very complicated because it has to describe the interactions of many different types of particles. So in fact, many people have been asking this question for a long time. Is this very supersymmetric, very nice-looking theory, could it actually be finite? And there was a historian of science who once wrote, "Reports of the death of supergravity are exaggerations. one year everyone believed it was finite, and the next year the fashion changed and everyone said it was bound to have divergences, even though none had actually been found. And that was Stephen Hawking who wrote that in 1994. And more or less the situation is still the same 17 years later. Most people think that supergravity is bound to have divergences, but it's still true that none have actually been found. So this theory, actually, there's a sense in which it fits into string theory. I mentioned that string theories have infinite towers. When you have a string, it can be excited in different ways. You can have different modes, different harmonics, like on a violin string. And those higher frequency harmonics get associated with a tower of sort of evenly spaced particles. But the lowest set of states are actually, in a particular type of string theory, are actually identical to those in this theory we're talking about, this point particle theory. So, but that doesn't mean that the two theories are the same. When you scatter gravitons off each other in this theory, it's not the same as scattering them in string theory, because in string theory you learn that the theory is not point-like when you go to very high energies, or you see these intermediate massive particles in it. On the other hand, you can still get some hints from string theory about the possible behavior of n=8 supergravity. But like many predictions of string theory, the results are a little bit ambiguous. There have been papers arguing that there should be no divergences until 9 loops, some saying no divergences at all. And the most recent consensus from string theory is no divergences until 7 loops. But the real way to investigate these questions is to actually calculate these scattering amplitudes loop by loop and see what's going on. So as I mentioned, in pure gravity, without any supersymmetry, the 2-loop calculation was what could be done around 1986. And it was found that pure gravity is badly behaved. It diverges and it's non-renormalizable at 2 loops. What was also known early on was that if you have these special supergravities, you have to work pretty hard before you have a hope of seeing the first divergence, because there are no divergences until you get to 3 loops. And these calculations turn out to be pretty difficult. There are tens or hundreds of thousands of Feynman diagrams once you get to 3 loops. And so that's why Stephen Hawking could report in 1994 that no divergence had actually been found, because nobody had been able to get to this level of complexity by then. But that was the prevailing wisdom then, which was that these theories would all diverge at this 3rd loop order. Well, we got into the game around 1998 when we computed not 3 loops yet, but we had to start with the 2-loop graviton scattering amplitude in this theory. And we were already guaranteed of finding something finite, so that wasn't surprising. But what was a little more surprising is that the theory behaved quite well in the ultraviolet at the very large values of this virtual momentum. In fact, it behaved just as well as one of these gauge theories, a particular gauge theory which is called n=4 Super-Yang-Mills theory. But you can just think of it as a cousin of quantum electrodynamics or the quantum chromodynamics that governs the strong interactions. In fact, this theory is known to be finite to all loop orders. So if supergravity is going to behave badly, it has to behave worse than this theory. And what we also found was a remarkably close connection between these two theories. Now, I don't expect you to understand any of these charts, just like when you read the eye chart at the optometrist, you're not really reading anything. You're just supposed to compare the two pictures. See, I went to the optometrist yesterday, so I remember this stuff. So you can see they're pretty similar, right? Which one do you like better, 1 or 2? I like gravity better. And if you're not colorblind, you'll notice that there are some green lines drawn on this one. And in quantum chromodynamics, the chromo stands for color. And so we always talk about gauge theory as having color degrees of freedom. And not surprisingly, the green color is supposed to characterize that. But what you'll notice between these two is that there's no color in gravity. So you have to wipe out the color to convert from gauge theory to gravity. And some things get squared. So you see there's this blob here, never mind what it is, but it appears twice as much in the gravity case. And there's a little S12 down here, and you see it appears twice as much. So there's some sense in which gravity is the square of gauge theory. And so we've been sort of exploiting those kinds of relations for a while now, first at 2 loops, and more recently at 3 and 4 loops. But the thing that you can also notice is that the black parts here are exactly the same. And these black parts represent certain integrals that are going to either diverge or not. But they're exactly the same integrals in both this gauge theory, n equals 4 super-Yang-Mills, and this gravity theory. And so what that means is that the 2 theories behave exactly the same, not only at 1 loop, but also at 2 loops in the ultraviolet. So we knew at 1998 about this behavior at 2 loops. And we also had some additional information that suggested that the first divergence would not actually be at 3 loops, but would be delayed to 5 loops. But at that time, we thought it would probably just diverge at 5 loops. But then in the meantime, there were some hints of even better behavior, and I can't really go into the details of them, but they motivated us to compute the full 3-loop amplitude in 2007. And then 2 years ago, we computed the full 4-loop amplitude just to see how they were behaving. In order to do that, we unfortunately had to exercise Feynman diagrams from our calculation because there were just way too many of them. So we had developed another technique, which we call the unitarity method, and it's based on the fact that scattering amplitudes are sort of special kinds of transformations between in and out states. But we also used a very close connection between the theory we were interested in, n equals 8 supergravity, and this other theory I mentioned in passing, a type of gauge theory. And the more general relationship is this: gravity is sort of like this square of gauge theory. This was actually noticed in another context by some physicists working in string theory. They sort of derived this at the leading order approximation. And what we've been trying to understand is how these ideas extend to the full quantum level, including all of these loops. I think I'll skip through these techniques, but there are various ways in which you can take these loop amplitudes and chop them into little pieces and recover all of the information by reassembling all the pieces. And it's kind of amazing that you can do all this without ever really writing down a Feynman diagram. But you can, and it's very efficient and very green because you recycle lower loop information over and over again as you build up the higher loop results. And in fact, the same kind of technology is actually used for state-of-the-art calculations for things that happen at the Large Hadron Collider in another kind of gauge theory, quantum chromodynamics. But the other aspect that we use is this idea that gravity is the square of gauge theory. So I just wanted to give another minute or two on that. We already mentioned before that the photons can come in 2 types of states, which if they're circularly polarized are right-handed with helicity +1 or left-handed with helicity -1. And the gravitons have the same property except their spins are twice as big. So you might think that you could somehow lay 2 gluons or 2 photons on top of each other and go from spin 1 to spin 2 through the ancient principle of 1 + 1 = 2. And it actually works. I mean, there's a little more to it than that, but what you can show, and this was first found by Kawai, Llewellyn, and Tai, but then there were a lot more sort of generalizations found by my colleagues. I should say that most of this work that I'm talking about was done in collaboration with Zvi Byrne at UCLA, John Joseph Carrasco, who was at UCLA and is now up at Stanford as well, Henrik Johansson, who's in Europe now, and Radu Roybon of Penn State. So 3 of them, Byrne, Carrasco, and Johansson, found some more general relations, which I can't really describe in detail here. But the basic relations look like this. They say if you scatter at tree level 2 gravitons off each other, it's like scattering 2 gluons, except you have to kind of multiply the 2 amplitudes around, and some of them get twisted up a bit, and you have to multiply by some other simple factor. But there are relations like this which actually exist for any tree-level graviton amplitude. And so if you've chopped your complicated loop amplitude up into little bite-sized bits, namely tree amplitudes, you can then use this information to work it out. So now, as of last year, Byrne, Carrasco, and Johansson were able to show that the 3-loop amplitude has the same optometrist chart, where you can flip back and forth between n equals 8 supergravity and n equals 4 super Yang mills. And even though it takes 10 to 100,000 Feynman diagrams to describe this process, the results can be cast, and we don't ever look at them actually, the results can be cast in terms of just 12 integrals here. And because of this form, we can learn some interesting things right away. In more recent work, which we haven't quite finished, we have recalculated the 4-loop amplitude in a new way, which respects the same kind of symmetry I was just showing you. In this case, instead of 12 integrals, there are 85 of them, which is too many to show, although 12 probably was too, but oh well, sorry. And what we can do more on the computer sometimes is analyze these formulas and look and see what happens. And what we find is that, surprisingly, exactly the same thing happens as happened at 1 and 2 loops. Namely, the behavior of this gravity theory, n equals 8 supergravity, continues to be exactly as well behaved as this special gauge theory, n equals 4 super Yang mills. And as I mentioned before, this theory has been known for a long time to be finite at every loop order. It goes back to work of Stanley Mandelstam from Berkeley and Howe, Stell, and Townsend. So either n equals 8 supergravity, our toy model for quantum gravity, is going to behave worse at some point than n equals 4 super Yang mills, or else it's also finite. So that's kind of the status in terms of direct calculations. But since the for-loop calculation was done in a different format, there have been various arguments that now say, no, it wasn't going to diverge at 3, 4, or 5 loops. It's going to diverge at 7 loops. So this is a little more of a challenge. And, but these are well-motivated papers, so we should try to look. But we can't go straight from 4 to 7 without passing through 5 or 6. And so our next task is to try to look at 5 loops, or at least my stronger collaborators might do it. But the point is that at 5 loops, the same kind of divergence that people are talking about here in the 4 dimensions we know and love will actually show up at 4.8 dimensions when we do 5 loops. Anyway, what I'm saying is that the 5-loop answer is a very strong indicator for what might happen at 7 loops, even though it's not a complete proof. And so there's work in progress trying to use some of these ideas we've learned about how gravity is related to gauge theory to see whether this theory could still have more miraculous cancellations in store. Now, I think I'm going to skip through some of this stuff because it's a little bit technical. And I'm just going to conclude by telling you again that we have not yet found any evidence that this point-like gravity theory behaves any worse than a theory that's known to be finite. And on the other hand, it's also clear that if you have to keep doing this stuff order by order, eventually you're going to get tired. And you need a new way to look at the problem. So we're trying to understand if there is some way we can make this slogan, gravity equals gauge theory squared, which is actually somewhat of a slogan. It's not something we understand as precisely as we would like to. But the question is there some symmetry related to that that might have to do with some of these mysteries of why these point-like theories of gravity are so well behaved? And of course, the bigger hurdle, if this theory turns out to look well behaved to all orders, is that it's still just a toy model. Those particles, 256 particles you saw, there's no way you can make them into electrons and quarks and gluons and W bosons. So you would have to do some more theoretical work in order to make it something that could become a real theory of nature. But it might point the way. So that's where we're at now, and thanks a lot for your attention.
Lance, if I could kick off the questions.
Sure.
You said that the n equals 1
supersymmetry.
Supersymmetry is now close to getting squashed by the LHC results or something like that. Is there a point at which the n=8 supersymmetry model might be tested in a...
Yeah, it won't replace it. It's more, as I was saying, this is sort of a toy model, and you would have to, first of all, it's much less compatible with reality than n=1. So we're not suggesting this in any way directly as some replacement if n=8, if n=1 supersymmetry looks like it just isn't explaining things. In some sense, you might say that would cast doubt on using any supersymmetry for any purpose at all, but our purpose here is to just try to understand whether, with all the theoretical crutches at our disposal, whether we can make gravity well behaved.
Just looking at some of those diagrams, they look like graph theory. Is this similar to graph theory?
Well, graph theory can be used to aid in all of it.
I mean,
For
graph
example,
theory is just a method of computation. But
graph theory is a method of enumerating graphs, and we need to enumerate graphs of various types. If you use Feynman diagrams, you have to enumerate graphs. And so you can use any tool from graph theory to count the graphs. And one of the important things is when you have so many graphs, you want to make sure you didn't count that one, and it was the same graph because it was so complicated. So Mathematica, for example, has a nice graph isomorphism facility in it, which will tell you unambiguously whether two graphs are really the same, even though you might have labeled them differently. So graph theory is very useful, whether you use Feynman diagrams or whether you use some other kinds of diagrams that we use, which are fewer in number, but you saw there were like 85 in this one case. So you still want to make sure you've counted them correctly.
yeah, you have to know how many nodes you have, and
Yeah, so there are various graph theory relations which you can always use as checks, which relate the number of loops to the number of external legs, the number of points emanating from each vertex, and so on. So can be quite useful.
Hi. Just looking at one of your first slides, the sort of classical way of looking at all of these different forces, strong, weak, electromagnetic, and gravity.
Yep.
Gravity is completely different from all the other ones on a classical level, because
Yep.
gravity affects the underlying structure of space, where these other ones are actually more like forces.
Yeah.
Gravity isn't really so much like those other forces. So why would you think that the same quantum mechanical approach would work for gravity that works for these other forces?
Well, that's another reason why there's been a lot of skepticism to this kind of approach. And I do have to say that this approach doesn't make manifest what you're saying, which is that gravity is all about the curvature of space-time, and the other forces aren't at all connected with this. We're taking what's kind of a more prosaic point of view. We're trying to put gravity on the same footing with the other forces and think of it in that way. What we're doing is we're perturbing, or we do small fluctuations in terms of these gravitons around a flat static background. So they are sort of quantum excitations, but they aren't really big ones. But they're what we can handle. And so we also don't try to study what is going on in curved backgrounds. And that's definitely another valid way to look at it. And studies of Hawking radiation and so on you can profit from that. And we're not addressing certain other paradoxes related to that, like how you count states of black holes, where string theory seems to be very successful. So this is just one sort of angle on the problem.
What computational tools did you use for your calculations?
Yeah, well,
Did you develop your specialized software for this?
Yeah, we have a fair amount of specialized software for it. So my colleagues use Mathematica, and I use Maple in terms of the symbolic manipulation languages that we use. But one of the things we have developed is this angle of looking at things by cutting graphs into pieces, because the individual pieces are often much simpler than all the Feynman diagrams. So what we need to think about and then implement in software is ways of having particles sort of scatter and rescatter, and what the kinematics of that are. So we will often build a guess for an answer, which might have lots and lots of parameters in it. But then we can fix all the parameters in the guess by probing around in this phase space of kinematics. So that's just some glimpse of some of the technical tools we use.
You were just talking about doing some of the calculations in the area of around black holes. I was wondering if you had actually done any Kerr-Newman calculations, whether the equations were separable.
No, I haven't personally done any real calculations in curved backgrounds myself.
We know that they're separable in some cases. Schrödinger's equation and a couple others separable.
Yeah, no, I actually didn't even know that, but I can imagine they might be, but thanks.
Famous paper by Brandon Carter.
Okay.
Hello, thank you.
Yep.
Great talk. My question is very pedestrian. I'd like you to define what you mean by toy model.
Oh, okay. So that's a model which we have no aspirations that it will turn into a theory of the world, but we like to play around with it because we think it's the best chance of possibly exhibiting a behavior that we would like to see. In this case, whether we could make the theory finite as a theory of quantum gravity alone. But we don't expect it to be a real theory of gravity and all the other particle interactions.
But it's mathematical.
It's a mathematical
Purely mathematical
theory.
with
and
with the
we
physics
don't try to fit
inlaid.
any parameters to physical.
Oh, so you don't assume any physics? You have to assume
Well,
some
we
physics.
assume some physical principles, general physical principles, but we don't try to fit parameters to any observed values, because
Okay,
the only parameter in this theory is the overall strength of gravity, and it sort of factors out of the whole problem.
Okay, thank you. That answered my question. Thank you.
I was just wondering if there's any classical model for this gravity equals the square of gauge theory, because I was thinking of like
No,
the
it's very-
Klein-Gordon equation is the square of the Dirac equation in some way.
It's very bizarre. You have to work hard to see it. So you mentioned the Klein-Gordon equation. So that's a wave equation, and you can derive those kinds of equations of motion from by varying a functional we call the Lagrangian. And you can write down a Lagrangian for gauge theory, and you can write down a Lagrangian for gravity. And they look totally different, and it's impossible to see where this thing comes from. You can try to, after you know it's there, you can try to redefine things in such a way to try to line them up. But it's really hard to see in the normal way that people think about classical equations of motion. There has been work in verifying it and proving it, but it involves more modern techniques which look at how amplitudes it's based not on sort of classical equations, but on putting all these amplitudes into one big space where they smoothly deform into each other, and then you can sort of build things up iteratively or recursively.
I have a kind of wacky question.
Yeah.
You said the one physical constant you were really working with is the constant of gravity, and I was wondering if you'd taken into that into account over low energy and large distances the effects of dark matter and dark energy on gravity.
Yeah, so that's sort of more realistic than we try to be. Okay. So you might say that dark matter is just some other particle that gravitates, and we have to put the particles that gravitate into these loops, okay? But we have one specific model, and the particles that gravitate there are the other 256 minus 2 particles, and they're all massless and there's special relations between the bosons and the fermions. And at the moment, we're more or less forced into that structure. And we don't have the freedom to get anything as rich as the real world of dark matter, let alone the real world of ordinary matter. But the hope is that if we understood things in this very simple setting, there might be some ways of tweaking the theory or modifying it to get other examples and maybe more realistic ones. But that's still very, very far out there. No clear picture how to do that yet.
Yeah, I have a question. Maybe that's a bit too large to answer, but could you comment on other tries to quantize gravity?
Yeah, there are a number of different approaches besides string theory. There is one example is called asymptotic safety, and it's the idea that although the theory might look non-renormalizable, that there's a way to fix it up if you take into account a number of different types of interactions. So the theory gets modified as you go to shorter distances in a particular way, that by the time you arrive at the end, it's all well-defined. So in principle, that makes some predictions. In practice, it's kind of hard to demonstrate it. So there's some preliminary evidence that something like that might be the right way to do it. And it's a completely orthogonal way from what we're talking about, but it might have some validity to it. So that was called asymptotic safety. And Steven Weinberg was one of the first proponents of that, but other people have been working on it a lot. So that's one thing. There's a kind of variation on it, which was proposed more recently by Petr Horžava, where he says that you can have a similar kind of flow or continuous change in the theory with energy, where when you get to these high energies, the theory actually does not have Lorentz invariance anymore. And so that's something that's very cherished, but maybe it's broken at high enough energies and is only restored as you come down to low energies. And then there's also loop quantum gravity, which is a notorious competitor with string theory, but I understand it very poorly. So, I mean, as of several years ago, they described some things related to the wave function of the universe, but they didn't have a very coherent picture of how you make gravitons at all, let alone exactly what their scattering amplitudes should look like. So it's a completely different sort of direction.
What about twistor theory?
Yeah, so, well, twistor theory itself, there are many different meanings of that word.
Penrose's approach.
Yeah. I don't know that the earlier versions of what he did gave to my knowledge, a picture, a completely consistent picture of gravity and quantum mechanics. Now, there are people who are working on some of these amplitude ideas who have adopted the twistor variables that he introduced as a way of understanding a lot of the patterns in these scattering amplitudes. So that part's has been pretty useful as a choice of variables, especially when you talk about scattering not just two gravitons off each other, but two gravitons go to many gravitons. Then the overall kinematics gets very complicated, and these twistors can help you sort through some of the haze.
Speaking of sorting through the haze, we have a coffee mug that will
wow.
hopefully contain something that will help you see through the haze a little bit.
All right. Thanks a lot.
Thanks very much.